Hi everyone, today we are going to talk about lesson 10.1. This lesson is going to talk about looking at sketching graphs and matching graphs to functions without using our calculator, as well as talking about real and complex zeros of our function. So if we look at the two graphs given to us on page 131, we see f of x and g of x, and we want to match without using a calculator which of our graphs which of our equations would match with our graph f of x. So we see that this we know is going to be an odd function because of this opposite end behavior. So right away we can eliminate some of these options that are all even, and that's actually going to leave us with just graph C that f of x has to be x to the fifth power minus 4x squared plus 2. Now, again, what kind of helped us eliminate that right away? Well, the end behavior is opposite, so we know that it has to be an odd degree in our polynomial. Now, that being said, if we look then at g of x, this end behavior is going to be in the same direction. So that is going to eliminate for us graph C, but because this is the same direction, we know it has to be even. Now, they are also both pointing in the upward direction, so that's going to get rid of anything with a negative leading coefficient. We also want to look at some key features, like for instance, we see that the y-intercept is at 2, so that's going to eliminate graph f from this possibility. And then we are kind of having it narrowed down to 2 pieces. Well, another thing we can do is test out, hey, which of these zeros are going to exist there? Because for instance, we see that 2 is a 0 on our graph. So if we plug that into these equations, 2 to the 8th power minus 4 times 2 squared plus 2, what we notice is that is not a 0 on our graph A. However, if we plug into our other option here, x to the 4, so 2 to the 4th minus 4.5 times 2 squared, and then plus 2, we do see that this works out to be a 0 on graph D. So this time graph D would best represent this, and again, that's x to the 4th minus 4.5x squared plus 2. And again, some features that we used the end behavior of the graph, we used the y-intercept, we used the x-intercepts. All of those helped us determine, hey, which of these functions would match up. Now, sometimes then we are going to be in charge of drawing these graphs, and sometimes that's going to be easier said than others. For instance, in this first graph, if I'm just trying to graph x plus 3, that's a line whose y-intercept is 3, and then we run 1 each time to get our graph of our line. So that we kind of know from prior math courses. All right, our next graph, however, is asking us to graph g of x, which is x plus 5 and x minus 5. So what the factored format is telling us is that we have 2 zeros. One of them is going to be at negative 5. The other then is coming at positive 5. And notice our leading coefficient out here is just officially a positive 1. Right? We don't really see it. It's just 1. And this is a second degree polynomial. Right? If we expanded that out, it'd be quadratic. So we know that our end behavior, because it is positive, will be pointing up, and it's the same direction since it is even. Now, last but not least, a common thing we can also find is our y-intercept, because if we plug in 0 for x, so let's use the store button here, 0, we're going to store that as x. We have x minus 5 times x plus 5, and again we plug in that 0, we end up getting that output value of negative 25. So again, we're going to 5, 10, 15, 20, 25. If we go down by 5 each time, we see this y-intercepts down here of our graph, and we have that quadratic. Now our next graphs down in C and D involve even more zeros. This time we have a 0 at -4, a 0 at +4, and a 0 at 1 if we plug all of these in to look at our points, our plotted points here. And again, this time we notice we have a positive leading coefficient, which means that as x goes to infinity, so will the y values. And then since this is an odd degree polynomial, we know it will have the opposite end behavior in the middle. Our y-intercept this time, again, if we store 0 as x, we end up, if we plug in 0, we end up with 4 times -4, which is -16, times 1, which means that our y-intercept this time is at -16. So down here, again, on our y-axis, there would be our y-intercept. Now, officially, we don't know exactly how high any of these maxes or mins will be without plotting some other points to test through, but we do know that it's going to have to come back down and pass through these zeros. So again, if we are just given the instructions to sketch our graph, okay, again, it doesn't have to be completely accurate with the maxes and mins without testing points, but otherwise we can kind of just sketch this in. Our last example this time is giving us 4 zeros, 1 at -2, 1 at +2, 1 at -1, and 1 at +1. So we have a degree 4 polynomial, right? We have those, if we expand it out, it would be degree 4, positive leading coefficient, so these are going up towards positive infinity. Our zeros, again, we plotted. We have a y-intercept this time at 2 times -2, which is -4, times 1 times -1, which is +4 after we plug all that in. Now again, as we pass through on this one, we don't officially have exactly how the maxes and mins are going to go. They can maybe go as low as that. Maybe we see one that goes low, one that goes high and short. Again, we are just sketching. We just know these behavior traits. We can't, without plugging in some points to test, know how far down those minimum values will go. We just know they will turn back. Now, what happens, though, if they give us the equation and it's not in that lovely factored form to know where the zeros were at? So all of these x-intercepts, if we set it equal to 0, we were able to find these zeros to plot on there. Well, sometimes we don't necessarily have that in that lovely factored form. Okay, but we could set it equal to 0 and find our factors, which eventually, if we set equal to 0 and solve, will tell us our solutions or our roots or our zeros, or if we see on the graph the actual x-intercepts that we plot. So a lot of these are going to be in reference to that term 0. They just have slightly different meanings depending on the context of when we were using them. And again, a lot of times how we're going to be able to find that is going to be by factoring. Now, we've talked a lot about these different types, difference of squares, factoring x method with a leading coefficient of 1x squared, if it's not 1x squared, and grouping. Right, we're also going to talk about sum and difference of cubes a lot today, but any of these are going to be possibilities to find, and of course, always look for a GCF if possible. So we're going to hop around on the next page then, on page 132, to see some of these different examples. Okay, for instance, if we start with letter B, we notice we have 2x squared minus 9x minus 18. So we're going to x method solve here and say, okay, what multiplies to be 2 times -18, so -36, but adds to be our middle term of 9. Well, that ends up being, what multiplies to -36 adds to be 9, -12, and +3. So we can take this middle term of negative 9, break it up to be negative 12x and negative 3x, and then we have that minus 18, and we group both of these, pull out our GCFs, and find our common factors here. So notice both of these have a factor of x minus 6, and then we have 2x plus 3 as the other factor. Now what they want us to do this time is find the real zeros. So this is the factored form. We want to then set equal to 0 each of these pieces. So we end up with x equals 6 and x equals negative 3 has, when we set each equal to 0, these would be our two real zeros this time. On the next one, we have a difference of squares. We have 5 squared, which is 25, x squared, which is x squared. So a plus b and a minus b would be our two factors this time. And as we set each equal to 0 to find out what our zeros are, we end up with 5 plus x equals 0. Subtract over the 5, x is negative 5. And then we have 5 minus x equals 0 on this one. Add over the x, we get x equals 5. So again, two options this time for our two zeros, 5 and negative 5. All right, our next example, we are kind of already in this factored form. We're essentially kind of being able to jump here to actually solve for our x. Reminder, when we square root, it's officially positive or negative when you square root 5 in this case. And then finally, we have two examples at the bottom for you to try. What would your two zeros be on E and 0 on F? All right, now notice on this next one, the instructions are still asking us to find the real zeros, but sometimes your answers aren't all the real zeros. What do I mean by that? Well, in letter A, we officially have, similar to letter C here, another difference of two squares. We're looking for our A and our B. Well, x squared is x to the 4th. 9 squared is 81. So we would have a plus b and a minus b as our two factors. And again, if we set this equal to 0, if we set each piece equal to 0 then, well, x squared plus 9 equals 0, we can't take the square root of a negative number and get a real answer. So this piece isn't going to give us a real 0. However, on the other side, if we set x squared minus 9 equal to 0, we have x squared equals 9, square root both sides. X will be positive or negative 3, again, if we're looking for the real zeros. This would give us imaginary or complex zeros, so we're not going to include it in our answer this time. And the next one, notice all three pieces have a GCF of x that we are able to take out, leaving us with x squared plus 2x minus 8. And then from there, we can x method solve what multiplies to be negative 8, but adds to be 2. Well, that's going to be positive 4 and negative 2. So as we factor this time, we still have that x on the outside, x plus 4, x minus 2. All right, we're allowed to just kind of jump to that step because this is a 1, x squared there. And then last but not least, when we set each piece equal to 0, there's officially x equals 0. We also have x plus 4 equals 0. And we have x minus 2 equals 0. So our zeros end up being 0, negative 4, and positive 2. So reminder that this GCF also has to be set equal to 0 just to make sure we get including that 0. All right, now our last two examples are what we have as the sum and difference of two cubes. Okay, and how I like to always remember this is SOAP. So it's similar to the difference of squares, except when you have this sign here, it's the same side as the original, opposite sign of the original, always positive. Same sign as the original, so these are both plus, opposite sign of the original, always positive. So if we look at letter C on page 133, we notice we have a negative here. And so we know this is going to end up being a difference of 2 cubes. X cubed is x cubed. 3 cubed is 9. So inside the equation, we have the values here of a minus b, because this is a difference. So x minus 3, same as the original. And then it goes a squared, a times b, b squared. So in this case, x squared, x times 3, or 3x, b squared, which is 9. And then same sign as the original, opposite sign of the original, always positive will be our factor there. Now these are always going to give you complex answers. So again, if we are looking for only the real zeros, the only piece we're going to have to worry about setting equal to 0 is this one here. So x is just 3. One more example similar to that. Okay, we have again our a and our b. X cubed is x cubed. This time 5 cubed is 125. So we have a and b, so x and 5, and then it goes a squared, a times b, b squared, a squared, a times b, b squared, same sign as the original, opposite sign of the original, always positive. Okay, again, SOAP, same, opposite, always positive. Okay, now let's jump to our last little section here. And what happens if we want to include those complex zeros? Well, there is this theorem that states with the fundamental theorem of algebra that the degree of our polynomial tells us how many complex zeros we are going to end up having. We have at least one of them in that system. So again, if we look here, notice this is a little out of order. You want to rearrange it so that it's in the correct order. X to the third, x squared, x constant. And we see that this is a degree 3 polynomial. So we know it's going to have 3 zeros of some sort. So we factor set equal to 0. This time when we set x squared plus 5 equals 0, because we're also looking for the complex zeros, we can actually solve using I to get those two imaginaries. And then our third 0 is going to have to be negative 1/2 on that. All right, now let's look at a couple more examples then on page 134 with this. Again, we are finding the zeros of the function. When it states it like this, we want the real and the imaginary. Any of them are going to be included. Okay, so this first one, notice we are going to look at, we have 4 terms. So this is a good example if we look at this chart of our factorings to use factor by grouping. So as we start solving on this one, again, we are going to group this up. The first group has a GCF of x squared. We're left with 3x minus 2. The second group has a GCF of 4. We're left with 3x minus 2. And this time our two factors, x squared plus 4, 3x minus 2. Now this time when we set each of these equal to 0, we are going to still solve now even this imaginary one. So when we take the square root of this negative number, instead of being positive and negative 2, it's going to be positive and negative 2i because we're square rooting a negative. On the other hand, over here, this is going to end up being a real 0. And as we solve, we get 2/3. So officially our three zeros are negative 2i, positive 2i, and 2/3. And again, that will match our degree 3, those three zeros that we have. All right, take a moment to try letter B on your own. All right, our final two examples of the day are going to involve a little bit more factoring. Again, first things first, take out that GCF if possible, because now what this allows us to do is turn this into a nice factoring problem. What multiplies to be negative 20 adds to be negative 1. Well, negative 5 and positive 4 will do that for us. So we have x squared minus 5x plus 4. And then reminder, when we set equal to 0, we have x equals 0, 5, and negative 4. Now you might be saying to yourself, okay, wait, this is a degree of 4. I only have 3 zeros. Why is that? All right, why do I only have 3 zeros, not 4? Well, this goes back to the idea of multiplicity, because what we notice is that this x was squared. So essentially, this 0 has a multiplicity of 2, and it's almost like it's taking up 2 out of those 4 zeros, and that's why we only ended up with 3, not more than that, to match this. So officially, it's because we're taking up 0 twice. All right, our last one, again, does have a GCF of 4 involved that we can take out. But what you're going to notice from here is that this still isn't our typical quadratic, because we have x to the 4th and then squared and then just a constant. So we've talked about problems similar to this before, but we could treat this like a factoring problem. What multiplies to be 2 that adds to be 3? Well, 2 and 1. But this time, when we do the plus 2 and the plus 1, instead of just calling this x, because of the 4 and the 2 this nature, we just make our x squared, and this is our factored form. Now, if we set this equal to 0, though, okay, if we set 4 equal to 0, this time that's not a variable, so that's not really going to do us any good. But then we have x squared plus 2 equals 0, x squared plus 1 equals 0. And as we solve on this, we notice we have positive or negative, because we're square rooting, we use positive and negative. The negative square root 2 would turn into an I out front, and then square root 2. On the other hand, when we square root, we're square rooting a negative 1. So this would be plus or minus the square root of negative 1, which is 1i, or just I on that one. So these would be our 4 zeros this time. All right, lots of information happening there. We will definitely be working more with these in class. Thanks everyone for watching.